All right, hello everyone. And let me share my screen. Welcome to the webinar on RLC circuits. And let's get started. So hopefully you can hear me, you can see me. And yeah, so this is one of my favorite topics because it's just so elegant and it's such a huge pity that it's not studied in A levels. It is studied in some countries. It is studied in the physics course, but unfortunately not in the UK. So let's try to remedy that. It's a very important topic because you um, you work with this every single, I'd say, minute. Every single minute you use something that uses an RLC circuit. My clock, my watch uses RLC circuits. My phone, some of the main components are RLC circuits. Everything you can think of that contains electronics uh, and some sort of transmitters, those are RLC circuits. Nice. So let's have a look at this circuit. This is an LR circuit. Why is it an LR circuit? Because it contains an induction coil and a resistor. It doesn't have a capacitor. So C stands for capacitor. So resistor, inductor, capacitor. And what's the behavior of this circuit once we close the switch? Well, if there was no inductor, that would be very easy. Yeah, you would expect something. You close the circuit, and the current would just jump. So the current versus time, and the current is 0, 0, 0, 0, and then you press the switch, and the current becomes EMF divided by R. That's what happens if you have no inductor. So no induction. But like honestly, this never happens. you never have steps like that in real life. That's not possible. You can always have a smooth curve. It could be very steep, but if you zoom in, it should be smooth. It should be something like this, and then a steep gradient, and actually going like this. But in an ideal scenario, it is a step. Now, what does the inductor do? Well, the inductor produces a voltage, an EMF, in the opposite direction, and that reduces the current. It uses the Lenz's law. So according to Lenz's law, the coil will induce an EMF such that to oppose the change in current. So the current is increasing. The current, and when you close the switch, the current is increasing. The coil will induce an EMF, as to reduce that current. So effectively what's going on the battery is plus minus, and the induction coil will produce a voltage in the opposite direction so that the current doesn't increase instantly with the induction coil. The current will increase gradually. The current, time, and it would go 0, 0, 0, and then it would go like this. And that is still EMF over R. That's the maximum current. You can see, no, don't call it terminating. This situation is current synonymous to flux. No, well, flux is proportional to current because flux in a coil is the magnetic field inside a coil, and flux is proportional to current. So yes, because when you have current in the coil, there's a magnetic field, and this magnetic field cuts the loops. Now, EMF is proportional to the change in flux, delta T. And you will see that this is the induced EMF. And as a matter of fact, the induced EMF is L di dt with a minus. The induced voltage in a coil is proportional to the rate of change of current. And if flux is proportional to current, that actually makes sense. So this is proportional to d phi dt. When we say flux, well, it's quite straightforward because a current produces a field. So the field is proportional to current, right? If you have a current, the more current you have, the more field you have around the wire. Flux is proportional to B, therefore proportional to current. So yeah, the flux in the coil is proportional to the current in the coil. But the induced EMF is proportional to the rate of change of flux, therefore is proportional to the rate of change of current. So the induced EMF is proportional to the rate of change of flux, which is proportional to the rate of change of current. I hope that makes sense. So the faster the current is increasing, the more voltage you would have opposing it. But once the opposing voltage is actually equal to the EMF of the battery, then you can't increase the current. So there's a limitation there. So basically, the inductor is pushing against the current. But once the current reaches the maximum level, the inductor has no effect on the circuit. Has no effect on the circuit. Let's see how that works. So we need an ammeter. We need an inductor. Oh, well, we need a resistor. We need a battery. And we need a switch. And we need some wires. So let's look at the current. So if I just flick the switch, you see the current increases like that. Now, if the inductor is not there, it just goes like a step. Okay. Can I undo? No, I can't undo. Okay. But if you have an inductor and you measure the current goes like this. Once again. How come the inductor doesn't oppose the change when you turn the switch off? When you turn the switch off, to answer this question, you first need to solve this problem from the assignment. This one, problem 9. Consider the circuit below. The capacitor is charged. Assume that the wires have zero resistance. When the switch is closed, the capacitor discharges through the wire. What happens to the energy stored in the capacitor? So this is a very important question. And the same thing, a very similar thing happens here. So the current is maximum, and then current suddenly drops to zero. Well, you've opened the circuit. It actually doesn't change abruptly. It actually does something else, which it's a bit hard to demonstrate at the moment. I think I can demonstrate it. To do this, I will need a different circuit. Okay. Remove the battery. Okay. So this circuit, so what's going on here? The battery passes the current through the solenoid, through the coil, and you see that the solenoid is reluctant to let the current increase instantly, but it also is reluctant to let it go. Look what happens when I disconnect the battery. The current drops to zero, but it doesn't happen instantly. Once it is disconnected, the current is decreasing, but it doesn't want it to decrease, so it keeps the current flowing for some time. Now you can't see it here. You can't see it in this circuit. I'll try to explain the reason at the end when we talk about RLC circuits. So bear with me on this one. Sorry, so that is a question. I'll post the question here. So everyone can see it. Is the same current going through the inductor and the resistor by K1L? Because if it is, then wouldn't the current be increasing in both components and energy wouldn't be conserved in the circuit? I'm not sure what you are referring to, because if we just take this circuit, the current is increasing. It's in the opposite direction. So the current is increasing. I wonder how it shows the direction. Just like that. The current is increasing in both, of course, but then it stops increasing. So in effect, the voltage here, voltage on the resistor is IR. The voltage on the inductor is minus L di dt. And here EMF is constant. So you kind of have to say that EMF is used up onto VL plus VR. So if, as the current increases, the voltage here decreases because the rate of change of current decreases. And as you can see, as current increases, the rate of change decreases. So current is increasing, but di dt is decreasing. Does that answer your question, Abiola? You have energy is conserved because one goes up, one goes down. Okay. Right, so basically a coil is a thing that doesn't like change. If you try to increase the current, it will fight you. If you try to decrease the current, it will fight you. And this leads to amazing, absolutely amazing results. Now, just for reference, the inductance of a solenoid is mu0 times the number of loops squared times the area of the loop divided by the length. So you have a solenoid, you have the cross-sectional area, you have the length L, and you have N is the number of turns of loops, and mu0 is a constant. Right, so you can work out the inductance of a solenoid. That's a good question. I don't remember the derivation of the formula, but that's not that important at the moment. Okay, so please look it up. Like, don't just trust me on this. I took this formula from the formula sheet. Because one of the problems requires you to use that formula. Now, energy stored in an inductor. If you think of it from the point of view of energy, like the battery is supplying power. It's supplying energy. The current is increasing. So some of the energy is, of course, dissipated through the resistor. But where does the remaining energy go? And if you look at this thing, you stop supplying the current, you stop supplying the power from the battery by flipping the switch, and yet the current is still running. That means that there's some energy. So the interesting thing is that the solenoid or inductance can store energy. And the energy stored, and this is shown in our assignment. I'll just quote the formula: energy stored. Energy in inductor is Li squared divided by 2. This is the energy stored in an inductor. This is the magnetic energy. Magnetic. And now it starts to make sense. The current doesn't increase instantly because the energy builds up in the solenoid. So the solenoid is a sink of energy. Energy goes into the solenoid, and once the solenoid is full, just like a capacitor, similar to a capacitor, once the solenoid is full, now the energy starts dissipating through the resistor. Okay, and same thing here. The solenoid stores energy, and then that energy is dissipated through that bottom resistor. So yeah, you can the area under the graph is current. Well, you can work out the energy stored. Okay. Now let's look at this one, this circuit. When in position 1, when the switch in position 1, the capacitor is charged. Capacitor charges. So this is positive. So positive charge flows onto the top plate of the capacitor, and negative charge flows onto the bottom side of the capacitor. The capacitor gets charged. Capacitor is charged. Now we flip the switch into position 2. Switch in position 2. Now the capacitor discharges through the resistor. Discharges. And here we can write a very simple differential equation. So we have a capacitor that is charged, and there is a resistor R. So using Kirchhoff's second law, the voltage on the capacitor has to equal to voltage on the resistor. Well, yes, because they're in parallel. Voltage on the capacitor is Q over C. Is charge over capacitance. And the voltage on the resistor is current times R. And now we can say, so the capacitor C, and then we can say, look, but current through the resistor is the rate of change of charge, because current is dq dt, is the rate of discharge. So Q over C is equal to dq over dt times R. But then we realize that the capacitor is actually discharging. So dq dt is negative, but this value is obviously positive, Q over C. So we have to use a minus here. And now we can write minus dq dt is equal to Q over RC. Separate the variables. So dq over Q equals minus dt over RC. And now I integrate it. And as limits, I go from 0 to t, and from initial charge, Q0, to final charge, Q. And that means I have logarithm of Q minus logarithm of Q0 equals minus t over RC. I hope you're comfortable with integration, and I don't need to explain anything further. So Q over Q0 is e to the power minus t over RC. Right, and then I have Q equals Q0 e minus t over RC. That is the formula for the discharge of the capacitor. Discharge of a capacitor. Now, if I remember that voltage on the capacitor is Q over C. And then if I divide both sides by C, I get Q over C equals Q0 over C E minus T over RC. But this is just simply voltage. So final voltage is initial voltage E minus T over RC. So that's the voltage on the capacitor. And then I remember that voltage is equal to IR. So current is V over R. So if I divide both sides by R, I get V over R equals V0 over R E minus T over RC. And that brings me to I equals I0 E minus T over RC. I've got three equations, and these are in the, obviously, they should be familiar to you. Sometimes on the assignments, it integrates between infinity instead of flux, for example. Well, if you know that if you go from infinity, if the distance goes from infinity to a given point, then you differentiate from infinity. Not exactly sure what you mean here. Like, it depends on this, on the circumstances. Like time, we're not interested. We're interested to know the charge at a given time. So we're interested in the final charge at time t. When we say final, it's not. When I say final charge, it doesn't mean after infinity seconds. No, it means after t seconds. So Q is final charge. That means after t seconds. T seconds. Whereas Q0 is the charge after 0 seconds. When you're talking about the potential energy, where is that? Well, yeah, you're interested in. You take the time as infinity, because if you look at this graph, it kind of goes on forever. And you're interested in the area under the graph, the total area under the graph. And that's why you have to use infinity, because there's no point at which you say, oh, the current is zero now, because the current is technically never zero. Like mathematically, it's never zero. Hope that makes sense. So yeah, this is what happens if you charge a capacitor, and I really hope you've you have a capacitor, you have a battery, you have too soon resistor. Okay, you have two switches, and then you just do that. Okay. So first of all, let's look at the voltage on the capacitor. So first you charge the capacitor, and voltage quickly becomes +9. And 9 volts. And let's run through the resistor. Okay, so now I open this switch, the capacitor is still charged, the voltage is 9, and now I discharge the capacitor through the bottom resistor. The voltage quickly drops to 0. Yeah. So the capacitor is now discharged. Now I can charge the capacitor once again, and then discharge it again. Okay, so you study this, and it shouldn't be a huge problem. Now, let's look at this circuit. If you look at this circuit, you have a capacitor and an inductance coil. So let's say you have, let's say the capacitor is charged. So you have plus, negative, and then you close the switch. Once you close the switch, the current through the induction coil increases. So close the switch, current increases. The induction coil will try to reduce that current. EMF induced in opposite direction. But now, once the capacitor is discharged, there's no more voltage to push the current forward. The voltage on the capacitor is 0. So the current starts to decrease. And what does the induction doesn't like? It doesn't like change. So current reaches maximum level. Maximum. but and starts to decrease. Starts to decrease. But the inductor continues the current. The current in such a way, so the capacitor is discharged, but the current is still running, and the inductor keeps the current running for longer. In that way, now this plate is positively charged, and this plate is negatively charged because the current flows to the other side of the capacitor. And then what happens? And then the process repeats in the opposite direction. The capacitor charges in opposite direction, in opposite polarity. Let's have a look. So we have an inductor, we have a capacitor. We need to charge the capacitor. So the capacitor is charged, and now we want to connect it to the, well, let's use a switch here and another switch here. Okay, so the capacitor is charged, and now if I measure the voltage on the capacitor, as you can see, the capacitor is charged. It's +9. And let's flip the switch. So when you close the switch, the current goes through the inductor, but then once the capacitor is discharged, it carries on, and so that it charges the capacitor in the opposite direction. So what we have created, we've created an oscillating circuit. And let's show this. Let's show this theoretically. So here, once again, we can say that voltage on the inductor is equal to the voltage on the capacitor. Voltage on the inductor, as we already know, is L di dt. And the voltage on the capacitor is Q over C. Okay. Now, when I make them equal, they actually opposite signs because, well, they are in parallel, so we can say that they're equal. I'm ignoring the signs at the moment because, well, I know they have to be, this is positive, Q over C is positive, so L di over dt has to be positive as well. And I know once I flip the switch, the current is increasing, so di dt is positive. So here, I don't need any minuses, even though I know that technically VL is L di dt. But once you go through this process, your mental process, like what is the actual sign? So the current is increasing initially. That means the voltage is positive, and Q over C is definitely positive. Therefore, I don't need any sign changes here. But I remember that di dt, that I is actually dq dt. It's the rate of discharge of the capacitor. And because the capacitor is discharging, this value is negative. So if I is dq minus dq dt, that means di dt is minus d squared q dt squared. It's the second derivative. So it's L minus L d squared q over dt squared equals q over c. All right. And now we have, I'll write it as q double dash equal to minus 1 over LC Q. Does this equation remind you of anything? Yes, SHM is x double dash is minus omega squared x. And as you remember, omega is the angular frequency. Okay, so I can assert that omega is square root of 1 over LC. This is the frequency of the circuit. And of course, I can write down T is 2 pi over omega, which makes it 2 pi square root LC. Sounds familiar as well, I'm guessing. Yeah, so period of a pendulum, period of a mass on a spring, also a very similar formula. So it turns out, so from here, we can say that period is proportional to L. So the bigger the L, the bigger the time period. And it's proportional to the capacitance. The bigger the capacitance, the bigger the time period. Let's check that. So let's increase the capacitance. If we increase the capacitance, you can see that the time period increases. The wave becomes wavier. If I decrease the capacitance, the time period increases. Similarly, if I increase the inductance, it increases the time period. And if I reduce the inductance, the time period decreases. Okay. So what we call this a simple oscillating circuit, or LC circuit. So we have a capacitor and an inductor. This is the capacitor and an inductor, and that's an oscillating circuit. And the time period of that oscillating circuit is 2 pi square root of LC. Okay. And now my favorite part. I always do this. I mean, if you have if you've seen my previous webinar on this topic, I've done this already. How to maximize frequency? Well, we know that this is an oscillating circuit. And capacitance and L. So time period is 2 pi square root of LC. If we want to maximize frequency, we want the time period to be as short as possible. So we need to reduce L and reduce C. Okay. C, so L depends on the number of turns, as we have already seen, the cross-sectional area of the loops, and the length of the solenoid. It's inversely proportional to the length of the solenoid. So you want to make it shorter. To C depends on the area of the plates and the distance between the plates. Okay. So how do you reduce C? To reduce C, make plates smaller. Make plates smaller. Secondly, move them further apart. Move plates further apart. I don't remember the formula for the capacitance. Something that I don't keep in my head. Capacitance of a capacitor. Formula. Parallel plate capacitor, so it's A over D. Seriously? It sounds a bit easy. Okay, E. I think it's epsilon 0. Yeah, epsilon 0 A over D. So capacitance is epsilon 0 A over D. Thank you. Epsilon 0. And yeah, so you want to make plates smaller, so reduce A and increase D. Okay, so let's draw. What do we get if we do that? So we make the plates smaller and increase this plate separation. Okay, so the capacitance decreases. Now, L, the inductor, to reduce L. Reduce N, reduce the number of loops. Reduce A. So the formula, we have the formula here. Mu 0 N A over L. Reduce N, reduce A, and reduce increase length. That's weird. Well, let's not worry about the increasing the length yet. Technically, you need to increase the length, but you'll see that it's really not important in this exercise. But yeah, reduce N, so we get fewer loops, and we make the loops smaller. Okay. Let's carry on. Why not move them even further apart? Why not move the plates like this? And then why not make them even smaller and then remove the loops altogether? What does this look like to you? What kind of device? Well, not necessarily a wire, very specifically. Maybe if I do like this. Ooh, yes, Archie, you got it. Antenna. Of course, it is an antenna. sometimes even looks like this with an inductor. Doesn't have to be. Sometimes it's just a stick. But yes, an antenna. Antenna is an oscillating circuit, and the wire itself is an RLC circuit. Yes, that is exactly how they produce radio waves, because radio waves have a frequency of from 900 kilohertz and above. So yeah, and exactly. So that's how you produce high frequency waves. Is you take a capacitor, you unbend it into a straight wire, and that's your antenna. Okay. Now coming on to, so antennas just RLC circuits, how they produce radio waves or really fast oscillations. Yes, but then why does the angle matter? Or does that have nothing to do with this and to do with polarization? The angle of the antenna, well, we call this an omnidirectional antenna, and this will produce waves that are polarized. So the electric field is up and down. Yeah, so this will produce a vertically polarized waves, but in all directions. You can have directional antennas which shoot a beam in a given direction. A horizontal antenna will produce horizontally polarized waves. That's why you will see sometimes you see several antennas for different polarization. Yeah. Okay. If you want to receive a signal and the electric field in the incoming electric field is horizontal, it will not produce oscillations in the antenna. Yeah, so how does a receiver work? So you have an antenna and there's an incoming wave, transmitted wave, and if this wave is vertically polarized, that means that the electric field is vertical. It will move electrons in the antenna up and down. So it will produce a current, an oscillating current in the antenna in the up and down direction. But if the polarization is horizontal, it will not produce a current in the antenna. Yeah. So that's why you have to have a horizontal. If you want to receive horizontally polarized waves, you have to have a horizontal antenna. Okay. Problem 6. Switch K is closed for some time, and the current is allowed to stabilize. Find the amount of heat that is dissipated in the circuit once the switch is opened. So let's have a look what's going on in this circuit. So when you close the switch, the battery starts, first of all, charging the capacitor. The capacitor becomes charged. And secondly, it starts building up current through the inductor and the resistor. Okay. And then the current reaches a maximum value. And the current in the capacitor reaches 0. Then once we disconnect the switch, now the capacitor starts to discharge through this. So let's have a look. Let's build this circuit. So we have a capacitor. We have a resistor. We have an inductor. We have a wire. We have a switch. We have a battery. Okay, let's close the switch. And as you can see, the current in the capacitor reaches 0, and the current in the resistor reaches a maximum. Let's do a voltage chart on the capacitor, of course. So let's see what happens when we disconnect the switch. The capacitor starts to discharge through the inductor, but now there's friction. Now there's a resistor here. Oh, interesting. We need to increase capacitance. We need to reduce inductance, and we need to reduce resistance. Okay, let's try again. Okay. Right, opening the switch. Reduce capacitance. Apologies. Okay. Charge. And open. Yes. Finally, what I wanted. Did you see that? Let's do it again. So charge the capacitance to 9 volts. And now switch off. An interesting fact, the voltage goes above 10, very briefly, but it goes above 10. That's an interesting fact. Let's reduce the resistance even further. Close the switch. Oh, wow. Okay, open switch. So it's oscillating, but the amplitude is decreasing. So if I can reduce that even further. Okay, let's try it again. Yeah, so something like that. The capacitor is charging very, very quickly. You don't notice it. It charges almost instantly. You close the switch, and it's charged, just like that. Yeah, it's exactly like a damped oscillation. Yeah, and that's the graph that you observe. You can have you can have critical damping, you can have over damping, or you can have light damping. So let's see. So basically, when switch is opened, switch is opened, the capacitor discharges through the L and R, and you have damped oscillations. The oscillations will die down once all the energy has been dissipated through the resistor. So the energy stored in the capacitor and inductor will be dissipated through the resistor. Effectively, it's a energy sink. This is the energy source, and this is the energy sink. But the capacitor is not an energy sink. A capacitor stores energy, and the inductor stores energy. Right, so that is quite interesting. So we want to find the energy stored in the capacitor. So once this switch is closed, the capacitor will charge, and the voltage on the capacitor will be equal to the EMF. So energy stored in capacitor is equal to 1/2 CV squared, and in this particular case is 1/2 C times EMF squared, because voltage on the capacitor is equal to the EMF. Now, once the current has stabilized, when the current has increased to a maximum through the resistor, the voltage on the resistor is IR, which is EMF. That means that the current, once the current stops changing, the voltage on the inductor is 0, and therefore the voltage on the resistor is equal to the EMF. Therefore, current times resistance is equal to EMF. That means that the current is equal to EMF over R. So energy stored in the inductor, energy stored in the inductor is 1/2 Li squared, and I know that the current is EMF squared over R, so it's 1/2 L EMF squared over R squared, and that's it. So the answer, so it's 1/2 C EMF squared plus 1/2 L EMF squared over R squared. That's it. You've got a very similar question in the assignment where you need to work out, it says the maximum, where is that? That's question 11. In the circuit below, basically what you have here, so the current through the battery, so the capacitor is charged, the inductor has current. So you need to find the total energy stored in both. And then imagine that all this energy goes into the capacitor, for example, and find the voltage on the capacitor. Okay, I hope that makes sense. So first you fill up the system with energy. So the current builds up, the current in the circuit builds up, and that's your stored magnetic energy. The capacitor charges, and that's your stored electrostatic energy. And once you disconnect, you only have the two energies. You have the electromagnetic and the electrostatic. Imagine that all this energy goes into the capacitor. Find the voltage on the capacitor, and you will see that it will actually be bigger than EMF. And that's what you saw here. You saw that the voltage can actually go above EMF if you have if the inductance is big enough. So let's see. When I disconnect the circuit, so I let the current build up, and you can see that the voltage actually goes well above EMF, which is quite cool. That means all the energy from the inductor goes into the capacitor, so it charges the capacitor even more, and then goes back. All right. But in your example, the resistance here is going to be 0. The resistance of the battery so you have a slightly different scenario. Okay, it's something like this. You can see that the voltage, the maximum voltage, is well above the EMF of the battery, which is 9, and the voltage is about 48. When the resistor is a superconductor, do we assume the current is equal to the EMF? Well, current can't be equal to the EMF. I'm not sure what you mean. Current is equal to the EMF divided by the internal resistance of the battery. Just like a short circuit. In any short circuit, if you take a AA battery and connect it to itself. Don't do it for a long time because it will get really hot. But you can do it for a short time. It will short circuit, and the current is equal to the EMF 1.5 divided by internal resistance of the battery. So yeah. Okay. So problem 7. When the resistor is but superconductor resistor is 0. Yes, but the battery is not a. You have the battery has resistance. If the battery doesn't have resistance, that's well, that's not possible. You will still have limiting factors. If you current, well, you need to understand the current will never go to infinity, right? So why would it not go to infinity? So either you're limited by the internal resistance of the battery, which limits the current. If that is not the case, then you have the inductance of the wires itself, because a straight wire still has inductance. And that would be the limiting factor for you. Even a superconducting wire will still have inductance because it's a wire. No, but if it's a superconducting wire, it doesn't have resistance, so that's not the case. No, you would be limited by the inductance of the wire, not heat. Okay, so for here, I just want to discuss briefly how to deal with this in terms of let's write a differential equation. So here we can use the Kirchhoff's second law, and we can write that voltage on the capacitor plus voltage on the resistor plus voltage on the inductor is 0. Now, of course, if the capacitor is discharging, so the current is going to be this way, that the EMF of the inductor is in the opposite direction. So it's going to be minus. And the voltage on the resistor is also going to be minus. Okay. So good so far, but there's still more to go. Voltage on the capacitor is Q divided by C minus VR. VR is current times R. That's all good. Minus, and this is VL, so this is voltage on this, so that's L di dt equals 0. And now we remember that I is minus dq dt in a similar fashion, so Q over C minus R d, so it's plus R dq dt plus L d squared q dt equals 0. And we have a differential equation q dot dot lq dot dot plus rq dot plus q over c that equal to 0. Let me check if I've messed up. Yeah, makes sense. And then I can divide both sides by L and Q double dot plus R over L Q dot plus Q over LC equals 0. I will call R over L, I will replace with gamma. After all, these are constants. And 1 over LC is omega 0 squared, or just omega squared. It's the frequency, angular frequency. So I can rewrite this as Q double dot plus gamma, Q dot plus omega 0 squared Q equals 0. This is a differential equation, and depending, well, we can write the characteristic equation. Right, so if there are three cases, first, if the discriminant, which is b squared minus 4ac, that is gamma squared minus 4 times omega 0 squared, if it's greater than 0, then you have overdamping. Okay. 2, if d equals b squared minus 4ac, and that's equal to gamma squared minus 4 omega squared 0, and that is equal to 0, then you have critical damping. And thirdly, if b squared minus 4ac is less than 0, which is gamma squared minus 4 omega 0 squared is less than 0, so then you have underdamping. Underdamped. So overdamping, as you might already know, looks like this. It takes a very long time. So if you displace, so Q and T, it just takes a very long time to discharge with no repeated motion. This is overdamping. Second, 2, that's critical damping. And underdamping, like this, 3, underdamping. So yeah, that is, this is the main idea. And then you have the solution. The solution you should already be familiar from the previous assignments on the differential equations. And so what does that mean? So if gamma is greater than 2 omega, that means omega is less than gamma over 2. That's in critical damping if gamma is omega is equal to gamma over 2. And underdamping is omega is greater than gamma over 2. Okay, so that's that. So gamma is the damping coefficient. Right, and it depends on the resistance and on the inductance, of course. Okay. I've done more of this. I've done more of this in the last year's webinar. So if you want to do some, you want to look at some other problems that I've discussed in the previous webinars, please do. Otherwise, I guess I'll finish here. And yeah, if you have any questions, please let me know. Lamassa, how are we supposed to write the proofs? As close to formal logical notation, yes. Well, you can use English sentences too as well, of course. Is Q the charge on the plates or cumulative charge? No, it's the charge on the plates in this particular case. Okay. All right. Okay. Yeah. Then see you all next week. Oh, sorry. Is it next week? Let me double check. I don't recall. Webinars. I'm guessing it is. Differential equations. RLC. Infinite sets. Yeah. I'll see you all next week. See you.